All right, I will record this time because I need to upload the videos on the YouTube as well. The channel provided by the NPTEL. So from here, we'll start our second week problem solving session. I will first introduce myself. I'm Vijay Rahane. Let me keep in the presentation mode. So this is Vijay Rahane. I'm a research scholar in the IIT Delhi as well as in the University of Queensland, and working on the material chemistry as well as the optoelectronics device and some sort of characterization. And I'm here to solve your questions based on the second week's the topic of the stereochemistry. And this topic is covered by the Professor Amit Basak. He is from the IIT Kharagpur. And as we have already seen in the first video, the layout of the courses. So here, let me we'll discuss the most of the questions based on the stereochemistry, enantiomers, diastereomers, epimers, anomers, and the heteroisomers. And I will try to upload these videos, all the PDF for all these three books on the drive. Probably you have access to that drive as well, as per my knowledge, right? So if you ask, I will send the link for the drive on this at the end of the session, so you can access that drive. So in that drive, I have uploaded the presentations. I will generally keep uploading the PPTs of the all the week doubt clearing sessions, so you can access from that. And also I will upload these some reference books for you. As we covered, the stereochemistry is very important in the organic chemistry. This is because of this quaternary carbon atom, and because of this quaternary carbon atom, the actual structures, chemical structures of the molecules is in the 3D form, not in the 2D that we generally write on the notebook. And these are some models. In this example, we have covered how the enantiomers and diastereomers are distinguished from each other. So one question someone asked in the discussion forum, what is mean by superimposable? So the superimposable and non-superimposable. See, if we have some material or some molecules like this, and we want to superimpose this on the same molecule which has the same type of arrangement. So if I move this molecule on the top of this, so it can be superimposed, or it can be fit as its original molecule. So this one is the superimposable, and if it doesn't get fit, see, if I try to fit this molecule on this second molecule, this one, so let's say this atom A and this atom B, this atom B will not get superimposed on this. It will not get fit on this. So we need to move the molecule. Then if you move the molecule, then also it will definitely not get fit in the molecule with any direction or any arrangement, possible arrangement we try to make. Then it will not get fit in this molecule or in the skeleton of this molecule. So this is the just superimposal. I have also texted him regarding some uh, pictures, so that with the help of that you can easily get idea about what is superimposable and non-superimposable. And these are some examples we have covered in the last week one doubt clearing session. So I will directly move toward the second week doubt clearing session problems. So this one is the question we have not covered, I think. Also, sorry, this one is the covered. I will take this question again. The respective number of chirotopy chirotopic stereo and the stereogenic carbon atom in the following molecules. So we need to cover the chiral carbon atoms as well as the stereogenic carbon atom. Stereogenic means if we change any atom by some another group, then that center will be converted into the chiral center, or the that carbon atom converted into the chiral carbon atom, right? So, and the chiral carbon atom also, as you know, it has the 4 atom or the 4 different groups attached. It has the 2 different and 2 same groups. Since if you change the one from these two, any atom, let's say if we have the A, and this is also the A, let's say this C, and this one is the D. So if we this molecule is the stereogenic carbon atom. This carbon atom is the stereogenic carbon atom, and if we replace this the same atom, any atom, let's say if I replace this atom, the A, by the different atom like B, so this carbon atom get converted into the chiral carbon atom, right? So this type of center, or this type of carbon atom is called as the stereogenic carbon atom. It means the by replacing one of the atom by the different group or the atom, that carbon atom get converted into the chiral carbon atom, that called as the stereogenic carbon atom. So we will see how many number of the chirotopic on the stereogenic carbon atom in this molecule. So we'll start with the first one. So in this one, we can see this. Sorry. One is the hydrogen, second is the bromine, and also the OH. These 4 groups are attached, and if you see this long chain, this fourth one is also different. So obviously, this carbon atom is a chiral carbon atom, right? So this is the one which is the, let's say I will label it as a C1. So this C1 is the chirotopic carbon atom, right? The second one, in this carbon atom, you can see the OH is one different group. This side, this entire as a one different group, hydrogen, and the second one, this all the 4 group are different, right? So this is also a chirotopic carbon atom. So C2 is also chirotopic carbon atom, and if you see this C3, it also having the OH, the group, this one entire group, as well as this one. So these 4 groups are different, right? In this one as well, you can see the carbon which has the hydroxy as well as the bromine, but the next side the carbon atom having the hydroxy and the entire different group. So these two are the different from each other. So this is also the one chirotopic carbon atom, and the other one, the last one, if you see the last carbon atom, we can see it also having the 4 different groups attached, right? So these all 4 are the chirotopic carbon atom. And obviously, if you change any of the atom, the chirotopic carbon atom are definitely the stereogenic, because if you change the any atom by a group other than these remaining, so definitely the final one, obviously the stereogenic center or the stereogenic carbon atom. So this is the answer, option A. You can see the 4 and the 4. This is the one example. The observed rotation for 10 gram of the, uh, actually someone forgot to mute. Can you, let me just check. Yeah, I think. Thank you. The question is the observed rotation for the 10 gram of the 2-methyl 1-butanol in 50 ml solution in 2 centimeter inverse polarimeter tube is plus 2.0 degree at 20 degrees Celsius. Generally, all these the optical rotation, we generally take the value as a 20 degree as a standard value, and the specific rotation of the compound we generally calculate. And the formula for the specific rotation is the alpha, that is specific rotation at 20 degrees Celsius. So it's general formula, which is equal to the observed rotation divided by length multiply by the concentration. So observed rotation is the 2.3 and the length 2 decimeter. See, it is written in the decimeter, right? So we need to take this as a 20 centimeter inverse. We need to convert it 20 centimeter, sorry. So we need to it's not centimeter inverse, it's centimeter. So 10 centimeter is equal to 1 decimeter. Just keep in mind, if you want to use some, if they given the values in the centimeter, we need to convert it into the decimeter. So you can use that into the decimeter. So it will be definitely the 2 decimeter multiply by the concentration. Also, we need to write in the gram per ml. So always see on the units as well. So don't forget to, it should not be gm, it should be g. So this is also the common mistake always people do in the writing the examination. Specifically, if someone write in the for the geoscientist examination, then always focus on these small mistakes. Gram, it should be the G, not GM. This is the incorrect way. So this is the correct way to write the gram sign. So the concentration should be in gram per ml. So gram per ml. This concentration should be the gram per ml. So they have given 10 gram, right, in the 50 ml. So we need to convert it into the 10 gram divided by 50. So this concentration we need to.
Hi.
Oh, sorry, someone. Let me just mute them. Yeah, I did. So the concentration in the gram per ml. So we can write it in the formula. So obviously it will be the 20. Sorry, 2, because we need to convert it into decimeter. 2 multiplied by 10 by 50. So by calculating this, you can see already given. So this will get, this one is the specific rotation of the compound. So in this specific rotation, always in the formula, this specific rotation, always we write the temperature as well as this D is for as the, I'm not sure why this D, but you can check why this D is here. So alpha is the specific rotation, and this alpha is the observed rotation. Sometime question may come, they will give the they will give the specific rotation. You need to find out the observed rotation. So you can play with the formula, and you will get the value of the observed rotation. May in the some competitive examination, you will find the, you need to find out the concentration as well. So you just need to write play with the formula to make whichever the value you want, so you can convert by that way. The next question is the methanolic solution of an optically pure compound A that show the specific rotation value, the specific rotation, that is alpha D, which is equal to plus 18.9 degrees Celsius, right? So at room temperature, that always referred as a alpha T, right? So which is equal to RT, that is room temperature, right? What will be the observation value at the same temperature if the solution of the same sample was made by dissolving 0.10 gram in 2 ml. So we need to find out in the this one value, that is concentration of the methanol, and then place in the 1 decimeter cube. So the we have the formula alpha is equal to alpha D is equal to alpha divided by the length in decimeter. So they have already given in the decimeter. So length multiplied by C. So which is equal to alpha is the that we need to find out, right? So alpha D they have given, which is 18.9, and what are the other values? The length they have given 1 decimeter, and the concentration they have given 0.10 gram per ml, which is 2 ml. So by solving this, you will get the value of the alpha. So probably I need to write in a straight way. So by solving this, this one, obviously, the one, there is no meaning of the multiply one. So this we can neglect here. And here you will get the value, some value. That value need to give, let's say the value will be x. So this value will be go on the left hand side. So 18.9 multiplied by x, which is equal to alpha. So if you solve this, you will get the value of this. So the value here, yes, here given by solving this, yeah, 0.95 degree. So just do some math and you will get the value by using this. You need to convert, you don't require to mug out this formula. If you remember this formula, that will also sufficient. So you just need to convert that. Length in the decimeter and the concentration gram per ml. So you can get the value of the any alpha or alpha D or the alpha, that is specific rotation or the observed rotation. So I'll just show some instrumentation. Why this alpha dash? What is this? So I have just purposefully kept here the slide. So see, this is the ordinary light. If you see the ordinary light, it generally has it generally transfer in the many direction. Whatever the random direction they have given. I mean, we'll see if we fix the bulb in the some cylindrical block. So whichever side is open, so that maybe we'll see the direction of the light in that direction. So probably you have seen the laser, which generally probably all know in the laser pointer. So in that one, they have just focused the light on the same direction. So that will be the in that direction which we are pointing. But still, that light which has the uh, electromagnetic nature of the light, we obviously know. So the electromagnetic nature, what is that electromagnetic nature? So this is light which propagate in this format, right? And also, let's say this is the one another axis. So it also propagate in this direction as well, like this as well. So it has very random direction in if you say in the XYZ axis. But if you use the polarized filter, so that direction will be the only this X direction. So only in this way. It will not be in any other way, other axis. So that's why this polarization filter we need to use, and we'll get the plain polarized light. That PPL we generally refer as plane polarized light. And how the optical rotation we generally measured. So we have a one light source, and that light will be the in the all direction. Generally pass that light through the polarizing filter, and so to get the our plane polarized light, and then we keep the sample in the sample tube. I will show the sample tube how this sample tube look like. So this sample tube which has the here the quartz. Sorry. Oh, sorry. So these two end are the quartz one, right? These are the quartz, both, and here there's some openings for the putting the sample, and which has the also the lead, or the you can see here the stopper here. So the sample generally fill in this tube. So here is the tube, which is generally in most of cases it will be the 10 centimeter long, which is we generally call it as a cell, or the polar what we call optical rotation measurement cell, or this. So we fill the solution, we dissolve in the some solvent, and the solvent should be obviously the solvent should not be the chiral solvent. So it is not like if we dissolve the solution in the chiral solvent, then obviously that we'll get this optical rotation due to the solvent, right? Because majority of the molecules will be the solvent molecules in the solution. So we fill this sample inside the tube, and we pass this ray, that plane polarized light, and we measure from this. Here there is a detector, and detector will convert into transfer that signal to the readout device, and we'll get in on the screen what is the exact value of the optical rotation. And so this is the cell. So this cell, you can refer, this one is the cell, and here there will be the analyzer. And this light, why this is getting rotated, because it passes through the optically active compound, so it will getting rotated by some degree. On that angle we generally use as a alpha, that is observed rotation, not a specific rotation. That alpha is the observed rotation. So if you put any achiral solvent, achiral sample, then we get the rotation. No, we don't get the rotation because the sample is achiral, so it will not, the sample doesn't have the ability to rotate the plane polarized light. So that's why that sample not able to rotate the plane polarized. So we'll get the symmetrical, the same line, or the same, you can see we'll get the same sort of light outside from the analyzer. We'll get in the analyzer here the same one. So this is the some instrumentation inside the instrument. So this is how the we measure the optical rotation. And yeah, this is the formula. You can refer this formula. So these are the question from the next week topic that we have covered. The Newman projection below represent. So this is the Newman projection they have given, and we need to find out the what is this Newman projection for. The options we have given the staggered form of the 2-methyl propane. So we'll write the structure of 2-methyl propane. 1, 2, 3, right? Propane, and 2-methyl means this is this methyl group. Sorry. So this is the 2-methyl propane. We'll see one carbon atom. The backside carbon, obviously the one. There is also one carbon atom, 3 carbon atom, right? So these are 3 carbon atoms, and which has the 1 methyl substituent. So if you write the structure will be like this. right? And the back side will be, there is one hydrogen, one methyl group, and one CH3 group. So this is the structure of the 2-methyl propane. So yes, this is the 2-methyl propane. And does it staggered? So what is the staggered and eclipse? We need to understand. So if this is your front carbon atom, and the backside carbon atom has the groups which is aligned in this fashion. Let's say it has A, B, C, 3 different atoms or the group, and the backside carbon atom has the D, E, and the F. All these are the groups are different. So if you see the structure, this carbon atom, they separated from each other by the 40 degree, 45 degree, right? Not 45. I think how much degree? 120 by 2, that is 60 degree, right? 60. They are, if you see from the front side, they are away from each other by 60 degree. This is the staggered conformation. And the eclipse one is the, if the front carbon atom is like this, and the backside group will be the same, on the same direction, right? So if you see, there is no any angle. This is just exactly backside of this one. So if you write properly, then definitely the we can see only the front carbon atoms, not the backside. So because they are covered by the front carbon atom, front carbon. So that backside, the same, that D, E, and F, these atoms are attached. So this is the eclipse conformation, and this one is the staggered conformation. So obviously this is the staggered one. So this is also the correct they have given. And 2-methyl propane. Yes, this is the 2-methyl propane. So 1, 2, and 3. At the 2 position, there is one methyl group is attached. This front side, let's say it has a methyl group, and 1, the back side of carbon atom is a 2, and this carbon atom has a 3. So it is a 2-methyl propane. So obviously the correct option is the A. That is the 2-methyl propane. Here you can see, this is the, yeah, you can see this is self-explanatory slide. So here you can see they are distinct from each other by the 60 degree and 180 anticlockwise rotation of the back carbon atom. So if you rotate this carbon atom in this fashion, so we can convert that structure into this, and then you can convert into Fischer projection formula. So our option is we need to just find out whether it is staggered or eclipse, and whether it is 2-methyl propane or the butane. So definitely it will not the butane. It has substituent at the 2 position. So this is 2-methyl propane. If anyone have the doubt, just let me interrupt in between. It is okay if you interrupt in between the solving question. The next question is, how many stereoisomers are possible for the molecule? So how many stereoisomers are possible? So first we need to find out the how many stereocenters or the chiral carbon atoms present inside this molecule. So if we write from here, so this obviously the not stereogenic or steric chiral carbon atom. This is also not chiral carbon atom. So we'll exclude some possibilities here, right? This is also not chiral because it has 2 CH2, right? So we have neglected. Now we have 1, 2, 3, 4. So among these 4, we need to find out how many chiral carbon atom. So this one has the one methyl and the other methyl group. These 2 groups are the same. So this is also not a chiral. So -1, In this one, if you see, it has a hydrogen atom. If we just write in this way, it has one hydrogen atom. So one second group is this CH2CH and this methyl. So this is the second group. Third is this methyl group, and the fourth is this carbon and the chlorine. So it has the 4 different groups. So this is the one chiral carbon atom, right? So we'll just rub it here and we'll focus on the another. Now this one, if you see, focused on this carbon atom, then it has the carbon atom which has 2 methyl groups, one carbon atom having the methyl group, one methyl group and one chlorine, and one carbon atom having one methyl and one CH2, right, and one hydrogen. So these all 4 are the different groups. So this is also the one chiral center, right? So these 2 are the chiral centers present in this molecule. And if you see this one, it having the same group. So this is also the not chiral carbon atom. So it has 2 chiral carbon atom. Just turn in this fashion. So yeah, I think it's good to turn, right? So this has the 2 chiral carbon atom, and we have the formula 2 chiral atom, the no element of yeah, that's also we need to consider the element of symmetry. If some molecule which has the chiral carbon atom, let's say these 2 are chiral carbon atom, but it has some plane of symmetry like this, then definitely this entire molecule will not be this molecule is not chiral carbon atom because it has the plane of symmetry, right? And if some molecule may have center of inversion, then also that carbon atom is a that molecule is the achiral molecule. So in this one, there will obviously there is no center of symmetry. So as well as the plane of symmetry. So this possibility get neglected. And so how many stereoisomers are possible? So the 4 stereoisomers are possible in this, right? So we have formula, right? That 2n, which is equal to that 2 is referred for, sorry, the n is referred for number of chiral centers, right? So we have 2 raised to 2 square, which is 4. Like this, we'll get the how many chiral carbon atom, sorry, how many stereoisomers are possible.
Yes, sir.
Please, any question if you have?
यार यहाँ पे पता ही नहीं चल रहा.
Where?
ये आती है 5 बजे अब तो. और मम्मी ने तो छोड़ दी चाय. मम्मी ने कहा नींबू पानी दे, चाय शाम को अच्छी नहीं बनाती. एक दिन 2 दिन ही छोड़ी है.
Dr. Sangeeta Talwar, can you please mute yourself? Let me just, yeah, thank you. So the next question is, which of the following molecule will not show optical activity? So the next question, we need to find out which molecule doesn't have the optical activity. If we'll look one by one. So if you see this molecule, it having the COOH group, or if we focus on this C1, let's say it has it's C1 and this one is the C2. So it has the carboxylic group, one hydrogen, one hydroxy group, and one group which contain the carboxylic and the hydrogen. So all these 4 atoms are different, right? So this is the chiral carbon atom, right? And this one also chiral carbon atom. This is not a chiral carbon atom. So obviously it has one chiral carbon atom and another achiral, but still, since because of this one chiral carbon atom, it is optically active molecule. The next one is it has methyl group and CD3. See, we have a rule like if there is a isotope, it also need to consider as a different group, right? Because this CD3 and this CH3 is different. If you see the atomic weights, then definitely this carbon 12 plus 2 plus, sorry, 2 plus 2, which is definitely the higher than this 12 plus 1 plus 1, right? So it's 15 and this is 18. So definitely the atomic weight of these two groups are different. The third group is the hydroxy and this fourth one is the hydrogen atom. So this is also an optically active molecule. The C1 is the C. It has the methyl, hydrogen, and the hydroxy. These three different groups are attached here, right? So this is the chiral carbon atom. And if you see here, it has the hydroxy, methyl, and the hydrogen. So all three groups are different. And this side is OH as well as CH3. This entire group is different. So this is also optically active. Right. The next, if you see the next, it is having the, we need to check, this is obviously the not chiral center, this A and this B. So the A and B, these are the two centers. At first glance, we will see this carbon may be a chiral carbon atom, these two. But if you see here, it has a, we'll check the configuration of one by one for this both two center. Let's say this one will get the first priority, this side chain will get the second priority, and this CH2 group will get the third priority. So this is S configuration, right? We are seeing from the upper side. So this will be the downward, this will be the upward, right? So this structure is in actual, if you see the structure in the 3D form. So I will draw it right in this here. So if you see the structure in the 3D form, this one is the bromine, and here downside there is the bromine. Upward is hydrogen, and here is the hydrogen. So in this one, if you see the from upper side, the first, second, and third, so it will be the anti-clockwise. It has the S configuration, right? And in this one, the bromine is downside. The second group will be focused on this molecule. Sorry, this center. Then the bromine is in the bottom side. The hydrogen is upside, right? Here there is the first priority will be the bromine here. Second priority will be the side group which contain the bromine atom, and third priority is the CH2 group, and obviously hydrogen is the fourth. If you look from the direction of the upside, from the side of hydrogen, then we will get the 1, 2, 3, right? This is the R configuration. 1, 2, 3. This is the R configuration, and which is having the hydrogen atom which is upside, right? So this is the R configuration, and if you see this R configuration, we need to invert because of the hydrogen atom is upside, so it is S. So the SS will not cancel each other, right? So additionally S plus S. So definitely it will be the final configuration with the S. So this is also the optically active. We need to find out which is not showing optical activity. So here in this all four example, we have seen only the chiral carbon atom and whether they have a chiral center, right? But we need to check also the two main factors, that is plane and second one is the center of inversion. Right. So we'll check one by one. Does it have any symmetrical plane? No, because these two carbon atom are having the two different groups. So there is no plane. Plane is also not there, and center of inversion also not here. So obviously this is optically active as it is. It is also having, there is no plane of symmetry or anything. So this is also not having the plane and not having the center of inversions. So obviously this is optically active. If you see this third molecule, then it having the, you can see the plane of symmetry. So we can't cut the molecule in the two equal part, right? So if you cut from this direction, the methyl, they are not identical, or they are not on the same side. But if you look at the center of inversion for this molecule, how we can look for the center of inversion? So let's say this is the methyl group at the top, of the molecule, and we'll see the methyl group, which is, we can see here, which is exactly at the bottom. So if you see this, let's say this is the center of mass of this molecule, and we can see that equidistance, there are two different groups, two methyl, which attach to two different carbon atom, which equidistance but opposite from each other. If you look at the hydrogens also, so this hydrogen are exactly at the equidistance and opposite from each other from the center of inversion, and also the hydroxy group. So it has the center of inversion, right? So this is the center of inversion, which is referred as or denoted as the I. So that's why this molecule is optically inactive. So the option C is the correct option, which not show the optical activity. So always try to remember the plane as well as the center of inversion also in account, because if we generally in the many examination we have a limited times, so we do just go through like, yes, this is not having this having the four different groups, so this is optically active, but also don't try to cross check whether it has the plane of symmetry or the center of inversion, or is there or not. Does anybody having any doubt? All right, we'll go to the next question. The next question is, on a Pluto where everything is frozen, all right, astronaut discovered two forms of 1,2-dibromomethane, sorry, ethane. We'll write a structure of 1,2-dibromomethane. So this is the bromine atom, and this is the bromine atom, let's say. Obviously, there are two hydrogen, right? 1,2-dibromomethane, gauge and the anti. Assuming that there are no rotation around single bond. So if it is frozen, right? So the to rotate this bond, we need some kind of energy. But if you don't get that much energy, that is in the negative temperature, we generally have found that the molecule doesn't have the sufficient energy to rotate the bond themselves. So the bond will not get rotate at the minus temperature. And in this condition, which of the following statement for the two forms is correct? So they have given, they are the enantiomers, they are the diastereomers, they are the mesocompounds, and they will show the optical activity. So in this first type of question, we need to find out the what is the lowest energy possible, because it's minus temperature, so molecule generally stay in the lowest energy for the molecule, or the lowest what we can say, the most stable conformation. The molecule will generally prefer to stay in the most stable conformation. And first they have given what they have given, gauche and anti. We'll write down the structure of the gauche and the anti conformation. So in the gauche conformation, let's say this is the front carbon atom, and which has obviously the 3 substituent we write here in this fashion. And another one will be the back carbon atom. In the gauche conformation, this bromine will be from 60 degree away, away from each other by the angle 60 degree. Right. So this is the gauche conformation. And I will just rub this one. And the anti conformation will be, which has the front 3 carbon atom as it is, front 3 atoms as it is, and the back carbon atom will be the bromine will be opposite from each other, right? And the hydrogen will be in the remaining 2 position available. So this is the anti conformation, right? So at minus temperature, the molecule will be prefer to stay in the most stable conformation, right? So if you see in this, which is the most stable conformation in this one? So this one is the most stable conformation, right? And this one is the most stable conformation. But if you see here, this one, this bromine and this bromine will be the anti to each other, and this molecule, this type of conformation which has the center of inversion, right? Oh, sorry, I think I did some mistake. I'll just yeah, here it is. And at minus temperature, they are these two forms are interconvertible. I mean inconvertible, right? So this form will not get able to convert into this another form, that is gauche cannot able to convert into the anti form. So because of this, the gauche and the anti conformation, they are the stereoisomer, but not related by mirror images. So this one and this one is not mirror images, obviously, right? Because their arrangement are different. And if you see the mirror images, obviously mirror, they will not be mirror images. And so they are the diastereomers. So these two forms are the diastereomers of each other. They are the chiral, although this one is the mesoform, but this one is the, if you see this molecule, this is not a meso, right? So this is the optically active form. This is the optically inactive form. So that's why this is optically active one form and this is optically inactive one form. These two forms are diastereomers. Diastereomers of each other, right? Any question? Yes, at room temperature, if you see, this 1,2-dibromo ethane will be in this anti form, or it will go in the gauche form. It has sufficient energy, so it can convert into one form to the another form. So you need to consider if certain molecule which has any possible form which is optically inactive, the entire molecule will be the optically inactive. although there are many conformations possible, but if the molecule has sufficient energy to convert into that type of conformation, so at that time the entire molecule or the entire solvent or the solution of the molecule of that chemical or the compound, which will be the optically inactive. So in this case, what happened? So although there is one optically inactive form is present, but the molecule doesn't have the sufficient energy to convert into that kind of form. So that's why this molecule is the optically active. And also these two forms are obviously the diastereomers of each other. So the correct option is they are the diastereomers of each other. Here the answer. Yeah, this is the just solution we have given. You can access the PPT from that link that I will text in the chat box at the end of session. Next question is the question: in the hypothetical molecule, the priority sequence for R and S notation. We need to give the priority sequence for this one. So first we need to find out which carbon they are talking about. So we'll see the which carbon, chiral carbon atom. This is the carbon and these two carbons. This is obviously not chiral. This carbon atom which has the hydroxy group, two hydroxy group. So this is, sorry, 3 hydroxy group. So this is not chiral carbon atom. And if you see here, this is, let's say, one group. This one is the next group. The COH is the third group. And CH, this is the four different, these are the 4 different groups. And we need to arrange this molecule in the order of the priority sequence rule. So what are the groups? I will write first. First group is the COOH. Right. So we need to check which is the how the priority goes. So first of all, we need to look at which is carbon atom, which having the functional group with the higher atomic number. So if you see this, it all having the carbon atoms, right? The 4 different group, which has the first atom is the carbon. If you see the upper one, which has the carbon atom, this is also having the carbon atom, and this is also having the carbon atom, right? This all 4 group having the first atom, which is the carbon atom. So at this stage, all are equal. Now we'll go to the proceed for the next atoms. So which is next atom? This is having the carbon, 3 carbons. It is having O, O, and O. This was having the 3 bond, the C, triple bond C, which is referred as C, C, and C. In this fashion, we need to consider it as a this 3 carbon atom is having attached, right? So we need to consider that in this way. Carbon atom which has 3 carbon atoms and it having the C double bond O OH. Since it having the carboxylic group, so this carboxylic group will get the first priority, right? Because it is a C double bond O OH group, that is C O O and another OH, right? So this is obviously get the first priority in this one, and the second priority will be in the carbon atom which having 3 hydroxy group. So the second priority will be carbon atom which having the 1, 2, 3. So let's say this is the C which having the OH, OH, and OH, right? So this group will be get the second priority. The third priority will be, we need to distinguish between these two groups. So the group which having the 1, 2, 3 carbon atom and group having the 1, 2, 3 carbon atoms. So if you see this group which having the alkyl CH3, right? And if you look at this, it is alkyne one, right? So obviously the third priority will goes to this carbon atom, that is C triple bond C, and the fourth one, which is carbon atom which having the 3 CH3 group. So we just need to match in this sequence. So which is the correct one? The COH, COO. This is correct. This one is the correct, and so obviously these two are wrong. After that, COOH, COOH. This is also correct. Oh, this is also correct up to here. Next, we will go for terminal. Sorry, this alkyne group. Yeah. So the option A is the correct option. So we can see from this one, the option A is the correct option. So we need to find out higher atomic number first, right? And then we need to check out the, in case of the atoms which have the multiple linkage, right? Then the atom which have the multiple bonded must be duplicate or the triplicate. Let's say it's double bond, as in carboxylic acid, that we need to multiply by 2, right? That is one oxygen atom, so it will be the 2 oxygen atom. If it is carbon, triple bond carbon, that is 1, 2, 3 bond. So definitely we need to triplicate this, that is 3 carbon atom. We need to consider that. So that's why the order will be in this fashion. The option A is the correct option. The next question is the structure of L-phenylalanine. So the D and L, probably we know D and the L. So we need to find out the L-phenylalanine. And this L-phenylalanine and D-phenylalanine, this capital L and capital D, these are the theoretical, right? And the practical one is the, we write in the form of small d and small l. Yes, if you have any question, please let me know.
Yeah. Sundar.
Yes, Naneshwar, if you have any question, please feel free to ask.
Yes, sir.
All right. So this D and L, that is theoretical notations, and small d, small l, these are the observed or the practical, right? So we need to find out theoretical D and L. So which is the L-phenylalanine. So the phenylalanine first we need to consider. So probably you guys know phenylalanine or structure of the phenylalanine. So the basic structure of the carboxylic acid is the basic structure of carboxylic acid we write like COOH at the most oxidized carbon atom at the top, right? And obviously there is one NH2 group as well as the one hydrogen atom, and that NH2 and the hydrogen atoms will be in the such fashion they are at the plane, right? Perpendicular plane. So here the exact NH2 and H. So this is the basic structure of the any amino acid, right? In this fashion. And here the side group will be the attached at this position. So depend upon which side group is attached. Let's say the side group is equal to hydrogen, then it will be the alanine. If it is side group is pH, then it is a CH2pH, then it is phenylalanine. And depending on any side group which is present here, the nomenclature will be like in this fashion. So can anyone tell how many natural amino acids present in our body? Anyone have any guess? So there are 22 around some amino acid trend. You can just Google it and you will get that answer. And also we are preparing for some examination like MSc entrance or JAM or NetGate or BARC, any exam. So for them also the amino acids and this topic is the one topic which is scoring topic. You just need to give 1 or 2 hours. So you will cover entire biochemistry or the amino acid chemistry or the protein chemistry in that topic. So probably I think you will find the video. There are 2 or 3 videos. I think 2 videos by for this amino acid and for the carbohydrate on the J chemistry channel. You can who are preparing for the exam, they can refer from there. So for us, we just need to focus on the stereochemistry. So we'll do. So first we need to understand what is the structure of phenylalanine. So the phenylalanine, the side group will be the pH and CH2PH, right? I'll just side group will be the CH2PH. So which amino acids have the side group CH2PH here given? So the CH2PH, 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 CH2PH. So obviously the all are the phenylalanine, right? Now we need to consider the stereochemistry. The structure of D and L. So the D amino acid which having the side group at so if you see here, first of all, we need to convert all the amino acid in which the COH at the upper side, that is most oxidized carbon atom, which should be at the top side, and NH2H in this fashion. So if you convert the all molecule in this fashion, so if it and this we can do by any two interchange, right? It is not like we'll do one interchange of the atom. Then if you do one interchange, that is if let's say if I say the example of this one, if I interchange these two atoms, then the configuration will be exactly opposite from this. So if we write here that NH2 and H, CH2OH, CH2PH, and COOH. So in these two molecules, this one and this one, whatever the combination it has, the combination of this molecule will be the exactly opposite because we have did only one interchange. So we need to do we need to perform two interchange to get the desired structure. So here, if you convert all the structures, so here we'll convert these two. So first interchange will be these two. So what we'll get the NH2 hydrogen and COH CH2 PH. Sorry, I did something mistake. Yeah, here the CH2 PH. Right. So in this one, we can see here the NH2 group on the left hand side. So this is the which amino acid? This is the D, right? We need to find out L. If you see this one, first interchange. Sorry, we need to make the two interchange, right? So this will be in the next one. NH2H, COOH, and the CH2PH. Right. So this one is the D amino acid. NH2 at the right in this one. So this one is the D. It should be the left, right? So this one is the D. If we perform the same in this one, let's say we have converted this one directly here, COOH, then hydrogen will become downside, and NH2 hydrogen. And in the second interchange, since we need to obviously the shuffle between these two, right? So if we do this interchange, then COOH, NH2, CH2PH, and the remaining one will be the hydrogen. So here also NH2 on the right hand side. So this is also the D. In this one, just rub this. The first interchange will be whichever interchange you can do. Just to make sure, you need to make the structure in which the COH will be the top side, right? And the CH2PH at the downside. That sorry, right. The attaching the CH2PH should be the downside, because in the generalized structure, the COH will be upper and the side chain will be the lower. And if the NH2 group on the right side, then that structure will be the, if NH2 on the right side, that structure will be the D amino acid, and the NH2 group on the left side, that structure will be the L amino acid. So in this one, we first convert interchange between these two. So NH2 COOH, the hydrogen and CH2PH will be remain as it is. And in the second interchange, so obviously these two are grouped in the position, so we need to change these two, CH2H, COOH, CH2PH. So see here also NH2 group is in the right hand side. That is, this is the structure of the D amino acid. And in this structure, we'll first do the first interconversion, COH at the top. So we'll keep that unaffected, and we'll interchange between these two, right? So if you interchange between these two, the CH2 pH will be downside and NH2 is on the horizontal line. But we need to do the two interchange, right, to get the structure. So NH2 H, COOH, and CH2, oh sorry, CH2 pH. Here you can see in this structure, the NH2 group is in the left side, right? If I write it in the good way. Here we did the interchange between the NH2 and H, right? So the final structure will be this one. So in this structure, you can see the NH2 group is in the left hand side. So this is the structure of the L-phenylalanine. Always focus on the structure. In this, if it is L, the NH2 should be the left hand side. And the condition is that the most oxidized carbon atom at the top and the side chain will be the at the bottom. Any question in this? Any doubt in the question? Please let me know if you are finding difficult to understand. I will try to improve some explanation. All right. If you don't have any question, I will just move to the next question. So the next question is which of the following picture projection is different from the other? All right. Someone has the question. Let me check. 3 exchanges allowed. You can do any number of exchange, but condition is that you need to do the even number of exchange. You can do whatever exchange you are. If you don't able to find out how many exchange, but just keep in mind that you should do the even number of exchange. I will show here with this some example here. I'll just add one slide. I think I will just change this. Right. Let's say you have one molecule. Let's say this is the one molecule, and if you do the only one exchange. So if you first we do the what is its configuration. So numbering will be the 1, 2, 3, and the 4, right? So the 1, 2, 3. So it is having R, which changes to S. Why it changes? Because the lowest priority group is on the horizontal line. So this is the S configuration for this molecule. If I do only one exchange, so see which exchange you want to do, whichever, if you do any exchange, whichever you want. So let's say if I did the exchange between the NH2 and H, so COOH will be remain as it is, CH2PH will be as it is, and then hydrogen and the NH2 group. This we need to exchange, right? So hydrogen will be go on the right side, and the NH2 group will be go on the NH2 group will be go on the right hand side like this. If you do one exchange, and now you see this will be the exactly opposite configuration it had. So this is the 1, this is the 2, and the 3. So 1, 2, 3. S, right? The S which changes to the R because of this hydrogen which is at the horizontal plane. So the configuration is the R configuration for this molecule. See, after one exchange, it is getting converted into the R configuration. If I do the another one exchange, any exchange on this molecule, we will get the exactly S configuration. Let's say any kind of exchange. If you exchange any atom, if you suggest anything, I will show the two different type of. Let's say if I exchange the. If anyone want to suggest me which exchange I should do, just write in the comment so I can do that exchange. So which exchange you want to saw in this structure, just let me know in the comment. If you are not suggesting, I will take two different kind of exchange. So let's see if I exchange. So there is no meaning in exchanging again this NH2 and hydrogen, right? Because already we have did a one-time exchange. If you do again one exchange, that will definitely get converted into the original form. But if you do the exchange between the COH and CH2, if I do the exchange between these two, the COH will be the go top side bottom, and CH2PH will be go the in this fashion, right? CH2PH and hydrogen. I did the exchange between the COH and the CH2PH. So now we'll check the configuration. This configuration will be definitely the S configuration. So if I do here NH2 2, and this one is the 3, right? So the 1, 2, 3, this is the R configuration, right? And the R, which is then changes to S because hydrogen is at the, that is fourth priority group at the horizontal line. So this configuration is the S, right? Which is exactly similar to the original one. If I do the different kind of exchange, now I have did here exchange between CH2PH and COH, right? If someone wish to exchange between this CH2 and the NH2, then I will show that kind of exchange. So let's say in this one now, I'm exchanging between the CH2 and the NH2. So here, this COH and the CH2PH, right? It is unaffected. Sorry, COH and this hydrogen will be unaffected, and we did the exchange between this CH2PH and the NH2. So the CH2PH will be go in the position of the NH2. So this CH2PH and the NH2 go at the position of CH2PH. So now you can see what is the priority here. The N will be a 1, 2, and the 3, right? So 1, 2, 3, it is R, which is then changes to the S because hydrogen at the horizontal line. So it is having S configuration. See, if you do the even number of exchange, the final configuration will be the remain same. But if you do the odd number of exchange, if you perform the any two exchange on this, then you will get the structure which having the S configuration. You can try it you will get the definitely the S structure with the S configuration. And if you do only one configuration, one exchange, it will be the R. So any doubt again? Please feel free to ask any doubt. So this session is especially for the doubt clearing. There are 3 exchanges allowed. You can do whatever number of exchange, but keep in mind, if you do the odd number of exchange, the configuration will be the exactly opposite. So you need to consider, you need to interchange that in the mind. So this combination should be the opposite one. So odd number of, don't try to, do the odd number of exchange, better to do the even number of exchange. And you need to feed the molecule in this form, in which the most oxidized carbon atom top. That is in case of especially amino acids. In case of especially amino acids, always try to keep the molecule in this fashion. Any amino acid in this fashion, COH always make it out at the top, and this hydrogen or NH2 will be the on this side, depending upon whether it is D or L. If it is D, then the NH2 will be here, and if it is L, the NH2 will be here. And the side chain, whichever the, let's say it is phenylalanine, then the CH2PH will be the downside, and any other tyrosine, tryptophan, that kind of amino acid, whichever the amino acid which will be the group will be the downside. Have you get the answer? Soumya, Shivani, have you get the answer? You can comment it, or we'll proceed for the next question. All right, so we'll proceed for the next question. Oh, why it is getting hang? Oh, I'm sorry, I think something happened with my system. So in between we will discuss. Anyone having the general question here? Yes. All right, I will share for the next question. Share slide for the next question. All right, I will cover this one in the last question. We'll cover, and then you can feel free to ask any question or any suggestion, anything, whatever you want. So the next question is, which of the following feature projection is different from other 3? Oh, just need to find out different from other 3. What does it mean? First one, we need to check whether all groups are correct or not, same or not, because the how to distinguish the first of all, it should be the same, right? It should the all attaching the atoms should be the same atom, right? So then and then we need to compare between the projections. So PH, OH, CH2H. So all right, so all having the same group. So this is obviously the same molecule. Only the conformation will be different. So which of the feature projection is different from other? So how to distinguish? We just need to assign R and S. If you assign R and S, then it is much more easy to distinguish from each other. So we can distinguish one from each other. Like let's give the numbering. So this is having the first, the PH will be the second, right? And the CH will be third. In this one, 1, 2, 3. right? So these are we have assigned the numbering to each atoms. So, and we'll solve the configuration, what is the exact R or S. So 1, 2, 3, it is R, which is changes to S. So S configuration, 1, 2, 3, which is R, then change to S, it is having S configuration, 1, 2, 3, it is having R, sorry, but it will not get changes to S because see, the hydrogen is on the vertical line. So this is having the R configuration, 1, 2, 3, which is R, which then changes to S. In this one, why we haven't changed this 1, 2, 3 R change? Why, although it is clockwise, why we haven't changed? This is because the hydrogen is on the vertical line. This is also one important point you always need to consider. If the hydrogen is on vertical line in the Fischer projection, then we need to check. We don't require to exchange that, right? Whether if it is R here, then we will keep that R as it is. So obviously the C option is the which of the following projections are different from each other. So obviously the C option is the correct option. Right. So these are some questions that I have taken or selected for solving to cover the concept from the week 2 topics which you have covered in the videos. So hope you have find these questions useful for your solving the assignments or in your future studies for in the field of chemistry, stereochemistry. So anyone having any doubt? So please feel free to ask any question, whatever you have. So we'll discuss that question. So the last time someone asked whether the 12th, I'll just stop the recording first.